Okay, here is the fifth video on quantum theory, based quantum mechanics, chapter 7 and chapter 8. Where I left off was I had painfully gone through and enumerated all of the quantum states. I'm going to bring this closer so you can get a better view of it. All of the discrete quantum states that fall out of the solution to the Schrödinger's equation, the wave equation, at various levels of the main quantum number, the driving quantum number, which is the quantum number of n. Okay. Now, what I want to do first, and then again, what this does is it enumerates all of the energy states mathematically that are allowed in an atom. And again, this equation was solved originally. In fact, so I think it's only been ever solved mathematically exactly for the hydrogen atom, but approximations to the math essentially are possible for all of the atoms, and you'll see that you'll see that as we go. Not the partial solutions, but you'll see that the same patterns and these same concepts apply to all atoms, not just hydrogen. Okay. Now, one of the key takeaways here that I want to just highlight for a second. I'm going to erase all of this in a minute, but I'm going to erase this all the gory details here on the right, and I'm going to leave the other two columns up here just so I can make a comment that these numbers are highly significant. It's highly significant that that as n goes up, the number of discrete states seems to go up by starting at 1, then 1 plus 3, then 1 plus 3 plus 5, and then 1 plus 3 plus 5 plus 7, etc. This is highly significant when it applies to the periodic table that you'll see coming at any point now. And again, all of this it's interesting. All of this kind of played a role and was developed by physicists. I think without even realizing how important it was going to be to chemistry. Honestly, I mean, and again, you'll see that as we go. Okay, now I want to take a quick little tangent and talk about shapes, because it turns out shapes are very important. The shapes of these orbitals, which again refers to the electron, the probability of electron being in a certain geometric space with respect to the nucleus, is highly significant with respect to chemistry. So it's important to kind of visualize these, or kind of be introduced to the visualization, because as we get into bonding, this becomes even more important. All right, I'm going to erase this now. And so, if you remember, I said that n refers to size. That's supposed to be a colon. L refers to shape without the a, and m refers to orientation. All right. So first, I'm going to ignore n for the moment. Again, n is just really kind of a size thing at the moment. But I want to kind of draw some of these shapes and orientations to give you a feel. And the book does a good job of this as well. But I'll try to explain, talk a little bit about it as I draw. Of course, I'm really pretty horrible drawer, as you know, but I'll do my best. So first of all, when L equals 0, the shape is spherical. Okay, all that means then is if the nucleus is here, then the shape of the electron probability density is essentially a sphere centered around the nucleus. Okay, essentially meaning that the nearer you are to the nucleus, the more probable the electron is there, and the further away from the nucleus, like towards the edges of the sphere, the electron can appear there, but it's less likely. Okay, so the electron is always drawn to the nucleus, but it can exist kind of anywhere geometrically in this sphere around the nucleus. And the spheres get bigger as n gets bigger. Okay, but when L is 0 for any value of n, the shape of the orbital is spherical around the nucleus. Okay. All right. Now, when L equals 1, the shape is, what do they call it? I think they call it barbell. I called it something else. What did I call it? I don't know what I called it. I guess I should look. I guess it doesn't matter. We'll call it barbell for now. Now, what that means is if we take a nucleus here, and I'm going to put some coordinates on here just so we have something to look at. Here's the y coordinate, the x coordinate, and there's also a z coordinate that goes, vertically or perpendicular to the board. The barbell shape means that the density looks something like this. I'm going to draw the one that goes in the y direction. It's kind of a little loop like this and a little loop like this, which essentially means that it's the electron is most likely to be in the area that's shaped by this little barbell. Interestingly enough, it means that it's not for this particular orbital, the electron is not likely to be that close to the nucleus. In fact, that the density actually drops down to 0 right at the nucleus, which is different from the first shape. The first shape, the electron is most likely to be very close to the nucleus. But in the second shape, that's not the case. And so one of the orientations of the barbell shape is to be oriented along the y-axis. Now if you remember, when you have L equals 1, you actually have 3 different orientations. So I'm drawing one of them here, one of the 3. The other 2 go against the other axis. So that's the L equals 1 orbital that goes in the x-axis. And then sure enough, there's also one that goes in the z-axis. So when L equals 1, the 3 distinct orbitals are actually shaped kind of like this. They're all symmetric around the center, but they have this kind of loopy shape. Okay, this is again all math. This folds out of the mathematical solution to the equation, but the math seems to indicate that the electron probability curve kind of looks like this. All right. And then last, I'm going to say last, but I may end up doing L equals 3 too. L equals 2 has a shape which is known as clover. And all this is happening as we go higher here is that these curves become higher order dimensionally geometric objects. Again, that's the real shortest way I can kind of put this. I'll draw it, but if you've ever seen mathematical functions like a third order a polynomial, and a fourth order or a fifth order, what you'll see is there's more bends in the curve, but you can see in going from a second order or third order to fourth to fifth to sixth that there's kind of a pattern there, and it's the same sort of pattern that we see in these shapes as they get more complex as L gets larger. So in the case of clover, I'm going to draw it also the y and the x, and I'll draw in the z. Okay, again the z is just perpendicular here. The clover ones, now if you remember, the orientation will have between -2 and +2, so there's actually going to be 5 orientations for clover. In the case of the barbell, it was a little easier to imagine 3, because in 3-dimensional space there's only 3 directions. And so there it's kind of easy to picture, okay, well the L equals 1 shape, the barbell shape, goes in the x in one, it goes in the y in the other, and it goes in the z in the third. So there's 3, it makes sense. But this one here, we got a shape that it actually has 5 orientations. It's hard to imagine that because now we're kind of going out of 3-dimensional space, mathematically anyway. But it kind of goes like this, is that I'm going to do a lousy job of drawing this one, but I'm going to draw one of them anyway. One of them looks like this. Okay? And so instead of it being kind of just 2 loops that we saw when L equals 1, it's actually kind of 4 loops. And one of these, like when m equals -2, will look like this. When m equals -1, it will be just flipped so that it's on the z and the x plane. Another one will be flipped again, and there's actually 5 of them. And what's odd about it, in fact, if you look at the pictures, is that one of the shapes for m equals 1, I think, is kind of weird looking. It's actually, it doesn't even look like a clover. It's odd. It has kind of a bulge in the middle. This is all just the math. This is what the math says, is that these are the shapes, and it all kind of fell out of the solution for the wave equation. Okay, and then it just gets crazier from here. L equals 3. I don't even what do you want to call that, but it's kind of a weird clover or something like that. And of course, for L equals 3, there are 7 orientations, not just 5. And it gets more complex from there. The big takeaway here, and when it comes down to bonding, which again this is where all this foundation really kind of is leading towards, is that really only these first 2 shapes, the spherical and the barbell, they're the most important shapes when it comes to bonding and it comes to most chemistry actually. These other shapes at L equals 2 and higher are less important in chemistry anyway. And so maybe that helps. Maybe that makes you feel good, or I don't know. But that's all I'll say about the shapes. I guess I'm going to end this one now and finally then say why all this matters, how it relates to chemistry, and the kind of the big moment. That'll be in the next video.